University of Wisconsin-Madison, and today I'm going to talk about how file systems differ, why this affects application-level crash consistency, and what we can do about it. It's a pretty long title, but the talk will be much shorter. So we store a lot of important information in computers. We store government records, medical records, personal photos, and so on. And because of this, we need computer storage to be reliable and robust. Computer storage should be reliable even if your computer crashes. Do computers still crash? Yes, they do. We still have data center outages from failing batteries, failing UPSs, and so on. We still have bugs in operating system kernels. And so in our research group, we took 11 different applications. These included databases, key value stores, distributed systems, virtualization software, version control systems. And we tried finding whether they keep their data reliable if the computer crashes. We found that none of them. Sorry. We found that none of these applications are completely reliable. In some cases, they had minor already known problems, like you need some kind of manual intervention before you could restart the application. And in other cases, data was corrupted, right? So this statement obviously requires some explanation, and that is going to be the rest of my talk. So in computer science, crash consistency deals with what if a system crash happens when you're trying to modify some data. In this case, we must make sure that the data is restored back to a consistent state after you reboot the machine. For example, if you are using a database and you perform a large transaction on the database and a system crash happens, you expect the effects of the transaction to be atomic. That is, after rebooting the machine and restarting the database, you want the database to be either in its old state or with the effects of the entire transaction applied to it. Crash consistency is an important problem in computer systems. It is a part of file systems. It is a part of database systems. Crash consistency is also incredibly hard to get right. Databases have been doing crash consistency ever since the 1970s, but the first serious crash consistency algorithm, Aries, was invented only in 1992, and even after that, it took 5 more years to prove it right. Fortunately, a lot of file system research has gone into file system crash consistency, and today's file systems use a set of standard techniques to achieve crash consistency, like journaling, copy on write, or soft updates. However, file system crash consistency deals only with internal file system metadata. For example, it makes sure that your directory entries are pointing to valid inodes. Now, the actual users of the file system, that is to say application developers and application users, are not concerned only about internal file system metadata. They care about their user level data. So what happens to this user level data when there is a system crash? To understand this, we did a bunch of studies, and in this talk, I'll be first going into a study about what guarantees do file systems provide applications that can be used by applications to achieve the crash consistency of their user level data. I'll be then going into a study we did that looked at a bunch of applications and tried to find out whether they implement crash consistency correctly using the guarantees that the file systems provide them. And finally, I'll be talking about a file system that we are working on right now that would help applications achieve crash consistency correctly. A preview of our results. So we studied 6 widely used Linux file systems: ext2, ext3, ext4, Btrfs, XFS, and resurface. These file systems had different configurations that made their behavior vary during a crash. We studied 16 configurations of the file systems. We found that the guarantees offered to applications varies even within different configurations of the same file system. And in fact, many of these guarantees are not by design, but are rather side effects of the exact file system implementation. And again, we looked at 11 applications. If we consider the applications, if we imagine the applications to be running on top of a very weak abstract file system, that is a file system that provides very weak guarantees to the applications, then these 11 applications had 60 crash vulnerabilities. If you consider a modern real file system such as ext3 or Btrfs, about 30 of these vulnerabilities can be exposed. So this is going to be the outline of the rest of my talk. I'll first start with an example that shows how much an application developer has to go through before they can achieve crash consistency of their application. So for the example, let us consider a file being there which contains a string a foo. Now, to keep the example simple, I'm going to talk about a file which contains 5 characters, but I want you to imagine that each of these characters actually represents a block of data. So we are talking about a file that contains 5 blocks of data. And let us say that we want to change the contents of the file from a foo to a bar, and we want to achieve this atomically with respect to a system crash. That is, if a system crash happens, we want to find the file to either contain a foo or a bar. Right. One way we might try to achieve this is by using a simple p-write system call, like I've shown here. I've shown the initial state of the file containing a foo, the system call itself, and the final state of the file containing a bar, right? Well, the p-write system call can result in many intermediate states if there is a system crash. Shown a few intermediate states here. The first intermediate state, only the first character of the system call has gone through to disk, and so you end up with a boo. And in the second intermediate state, the last 2 characters have gone to disk, but the first character has not. There are many more intermediate states possible. So what do you do if you need to do the change atomically? There are many different ways. Let us consider one particular way of doing this: rollback journaling or undo logging. In rollback journaling or undo logging, what you do is you make a backup of the existing content of the file that you are going to modify. You make the backup in a log file, right? And then you modify the actual file, and finally you delete the log file. The idea is that if a crash happens in the middle of updating the actual file, then you can always recover the old state of the file from the backup. So here I have shown the same steps converted into a sequence of system calls. I am going to call this sequence of system calls an update protocol. We first create the log file. We take a backup of the actual contents to the log file. We record the actual data and the position of the actual data that we are going to modify. And then we do the actual overwrite of the actual data. And then we finally delete the log file. Now, this particular sequence of system calls works correctly if you are using the ext3 file system under a particular configuration, the data journal configuration. I've shown a few intermediate states that might happen, if a system crash happens with this particular file system configuration. In the first two intermediate states that I have shown, the log file has not been completely written to. So in this case, when after rebooting the machine, you can detect that the log file has not been completely written, and you can simply delete the log file. In the third intermediate state that I've shown, the log file has been completely written to, but only part of the actual modification has taken place. In this case, after rebooting the machine, you can recover the old state of the file from the log file, right? Now, this sequence of system calls does not work for crash consistency if you're using another configuration of ext3 known as the data ordered configuration. Because in this particular configuration, ext3 can reorder these two system calls and send the overwrite of the actual file to the disk first before it sends the write to the log file. I thought it was a bit ironic that the configuration called the ordered mode reorders things. But anyway, in this case, you might actually end up in an intermediate state where you have never written anything to the log file, but the override of the actual file has started. And so recovery is not possible. So to make things work on top of the ordered mode of ext3, you will have to add 2 fsync calls to make sure that things do not get reordered. Now, even with the fsync calls added, this sequence of system calls does not work on top of yet another configuration of ext3 known as the write back mode. That's because a crash at this point in this configuration can lead to a state where your log file is filled with garbage. In this case, after recovery, you would not know whether the log file is filled with garbage or with actual data, and you might end up recovering the garbage data, which is of course wrong. And so you can solve this problem by adding a checksum when you take the backup of the data and making sure that you are recovering the actual data and not garbage, right? Now, even if the checksum added, according to the Linux man pages, this sequence of system calls is not sufficient to achieve crash consistency. This is because, according to the man pages, this particular sequence of system calls might result in a state where the log file has never been created. What you have to do is you'll have to add another system call, another fsync to the actual directory that contains the log file to make sure that the creation of the log file has been sent to disk, right? So this particular sequence of system calls will work in all file systems. I believe it would. But remember, that sequence was only to achieve atomicity. If you want the change to be durable by the time the sequence of system calls is done with, you need to add yet another fsync call, right? So to summarize, file systems vary a lot in the kind of guarantees they offer applications with respect to crash consistency. And applications usually depend on some of these guarantees to work correctly. For example, if a file system does not reorder things, then the application would work even if you don't issue fsync calls, right? So the next part of my talk I'm going to is about a study on what kind of behaviors, what kind of guarantees do current file systems offer to applications. I'll be first talking about the methodology of the study, and then I'll be talking about the actual results. So in order to study the behavior, we consider the relevant file system behavior in terms of persistence properties of file systems. Persistence properties are properties like if you issue a write system call and a system crash happens, is the write system call atomic? So we have a bunch of atomicity properties that corresponds to different system calls. Similarly, we have a set of ordering properties. If two different system calls are sent to disk, are issued to the file system, would they be sent to disk in order, or would they be reordered before they are sent to the disk? So again, we studied 6 Linux file systems, 16 configurations of the different file systems. So how did we do our sorry?
So is it 16 per file system? Or?
No, it's a total of 16, yeah. So we, how did we do the study? We first ran a particular workload that would stress the persistence property that we are trying to examine. For example, if we are trying to find out whether write system calls are atomic, we can issue a write of 8 KB. And while this workload is being run, we record the trace of the blocks that are being sent to the disk by the file system. And from this record of block level trace, from this block level trace, we can calculate the various disk states that are possible, disk images that are possible if a system crash had happened during the workload. So what is a list of disk states that we calculate? We can calculate and reconstruct these disk states. What is the sequence of disk states that we reconstruct? Well, the disk has a cache within it, and this cache can also reorder things. We reconstruct all the disk states that are possible if the disk cache never reorders, and we reconstruct a few states that are possible if the disk cache does reorder things. Now, after reconstructing the disk images, we run file system recovery on top of them. That is, we just like remount those disk images, and then we verify whether the particular persistence property that we are testing is satisfied. That is, we verify whether the write system call has been performed atomically or not in top of each of the disk states. So these are our results. Uh, the rows represents the different file systems and the configurations of the different file systems. And the columns represent the different persistence properties that we tested. For example, this particular column represents whether directory operations like rename or unlink are atomic with respect to a system crash for these file systems, for each file system. Now, in this table, if we see a cross mark, it means that we reconstructed a disk image where the persistence property was not satisfied. So ext2 does not satisfy the persistence property. Directory operations are atomic. However, if we do not see a cross mark, it simply means that we did not reconstruct a disk image where the persistence property was violated. So it is only likely that the file system satisfies the persistence property. It's not a guarantee. I'm not going to go into the details of the results, but overall, the main thing to note is that file systems vary a lot in the kind of guarantees that they give. So in conclusion, applications should not rely on these persistence properties, on the guarantees that file systems give to them. And the methodology of testing applications on top of a particular file system to make sure that it works right after a system crash is not sufficient. If you change the file system underneath, your application might not work any longer if a system crash happens, right? So after this, we studied applications and whether they actually implement crash consistency correctly. I'll be first talking about the methodology we use to study applications and the results of our study. So in order to study the applications, we constructed a tool called ALICE, the Application Level Intelligent Crash Explorer. The purpose of ALICE was to study the correctness of application level crash consistency for a particular application without assuming a particular file system underneath. We wanted to find out what all can go wrong on top of any file system, right? And then we wanted to relate each of the problems that we find with the exact source code lines associated with the problem, and also the exact file system behavior that might lead to the problem, that might lead to exposing the problem. So this is how ALICE works. We first apply ALICE with a workload of the application. For example, if you want to examine a database, we can supply a workload where the database, where a transaction is performed on the database. ALICE runs the application and gets a system called trace. ALICE has within it an abstract persistence model. An abstract persistence model is a model of a file system that defines all the possible crash states for a given sequence of system calls in that file system, right? So by default, ALICE uses a weak abstract persistence model that models a file system which provides very few guarantees to the application. However, ALICE can be customized with the abstract persistence model of a real file system. For example, we could use the abstract persistence model of the data journal configuration of ext3 that would not reorder system calls. Right? The next step in ALICE is an explorer. The explorer uses the system call trace obtained from the application and the abstract persistence model to construct a few crash states, a few disk images that can happen with this system called trace and with this particular file system that is modeled by the abstract persistence model. And Explorer selectively targets the crash states that are related to the atomicity and the ordering of different system calls. Right? Once we reconstruct each of these crash states, we run the application again on top of each of these crash states. Right? And we check whether the application is still consistent. So if our workload was a database transaction, we simply run the database again and make sure that the database is atomic. The transaction was done atomically. Right? And from this, we will come to know which crash states are recovered from correctly by the application and from which crash states the application could not recover from correctly. And that helps us point out which system calls are related to incorrectness and what file system behavior can expose these incorrectnesses and so on. So this is the list of applications that we studied. 2 distributed systems, 1 virtualization software, 3 relational databases, 3 non-relational databases, and 2 version control systems. And I'm going to show you the kind of results that Alice produces. So this is the list of system calls. This is the protocol used by Git, if I may, that achieves crash consistency, right? And Alice tells you if this rename call were not done atomically, then Git would not be consistent after a system crash. Similarly, if these system calls are not ordered automatically after each other, if the file system decides to reorder them and a crash happens at an inopportune moment, then there can be problems, right? And so these are our overall results. We find a total of 60 vulnerabilities across all the 11 applications. Many of them result in silent data losses and loss of availability, which means you need some kind of manual intervention before restarting the application. So what if you use an actual file system, for example, Btrfs? These are our results with Btrfs when we configure Alice with a Btrfs's abstract persistence model. We found that there are 31 vulnerabilities that are exposed on Btrfs. So a sampling of the kind of patterns that we observe on which file system behavior contributes most to the vulnerabilities. So some of the modern file systems implement some heuristics. They explicitly guarantee a few things to applications to make sure that applications work correctly. One of these guarantees is flush before rename. So if you take ext4 and if you do a rename, it automatically flushes all the data to the file before sending the rename to disk. We found that very few of the vulnerabilities that we found are helped by these heuristics. Of course, we examined only a certain class of applications. There are other applications for which the heuristics might be more useful. We found that the fact that file systems can do non-synchronous directory operations actually affects a lot of applications. We found that the behavior of file systems like ext3 write-back, wherein you can find your file filled with garbage, affects a few applications. There are a lot more results in our paper. I was supposed to have a link to the paper here. I can provide it later. But yeah, we have a lot more results in the paper that I will not be going into detail about. We have an in-depth analysis of the kind of file system behaviors that affects applications. We have the list of vulnerabilities that are exposed on top of other abstract persistence models of real file systems. We have a lot of interesting, we have a summary of our interesting conversations with application developers when we reported all these vulnerabilities. And we have a note on how not to interrupt our results that essentially is because showing this graph at some conference led to a flame war between different application developers. And so that's the part of the talk that talks about the problems. Now finally to the solution. I'll be first talking about the idea and the overview of the solution, and then I'll be talking about the design and challenges. So how do we improve the current situation? One observation is that a file system that does not reorder anything at all is very good for application level crash consistency. In fact, if you use such a file system, only 10 out of those 60 vulnerabilities are ever exposed. And of course, for this 10, you need some amount of minimal atomicity properties, like renames should still be atomic. I wouldn't read much into that. And this fact is obvious in retrospect, the fact that you need file system ordering for applications to be correct, right? Um, for one, programmers are used to sequential execution, and the fact that things can get reordered is it's hard to imagine and hard to code for. And the second is process crashes, pressing Control C happens a lot more often than system crashes, and applications are usually well adapted to recover from process crashes. Process crashes expose a lot of things except for reordering system calls, which can happen only during system crashes, right? So our idea is if you use a file system that preserves ordering, then application level crash consistency is sort of a solved problem. And there are some file systems that already preserve order. There is ext3 and ext4, for example, with the data journaling mode. So why not just use these file systems and be done with it? The problem is that these file systems that preserve order have a basic performance problem, which I'm going to call global ordering. What do I mean by that? Let us consider two different applications. Application A, which is say a background application, maybe someone is copying a video file. Let's say it writes 150 megabytes to the disk. And then application B, which is a foreground application, an interactive application maybe, writes two small files like 10 bytes or so, and then calls fsync, right? Now, if you need global ordering, in a file system that preserves global ordering, if you use a hard drive, you end up with that particular fsync of the interactive application taking 4 seconds. Because the 150 MB that the background application wrote has to be ordered before these 10 bytes of important data. And this slow fsync is a basic problem. It's not related to the particular technique I use to achieve ordering. It does not depend on whether I use journaling or soft updates to achieve the ordering. It simply is the simple fact that you promise global ordering leads to this performance problem. Another way to put this is you have some additional orderings that are being preserved more than what you need, and these are orderings between independent applications. So our solution is to have different streams. Each application is associated with a particular stream, and you order only within that particular application. You order things only within that particular stream. So if I do something like this, if I put application A into one stream and application B into one stream, then you can, that fsync would take only 60 milliseconds. Again, on a hard drive, of course. So the idea seems simple, and designing it, like implementing it, should also be simple. All the file system crash consistency techniques that already exist, journaling, copy on write, soft updates, they let the file system developers define ordering between the different disk blocks. So you can just impose the ordering that you require from streams on top of the file, on those existing crash consistency techniques, and you're done, right? That doesn't really work. Why not? So the first challenge is that file system crash consistency already requires some ordering on metadata updates. To explain this, consider a file. A file is going to, in a traditional file system, it is going to have an inode pointing to a sequence of disk blocks. Let's say that the user comes in and says that the file should be truncated. So the inode would have initially had pointers to the various disk blocks. All those pointers would be removed. And now let's say the user in some other application decides to create a file, right? So you make another inode valid. and then the user appends some data to the file. In this case, the file system has to allocate a particular data block to the inode, to the newly created inode, and so let's say the file system uses the data block that is that has been deallocated from the other file, right? Now, all these things happen within memory, right? The removal of block pointers and the addition of block pointers to the other inode, all these happen within memory. Now, what if this block pointer manipulation is reordered when you send it to the disk? In that case, you might end up in a state like this, wherein two different block pointers are pointing to the same block because the allocation of the data block to the second inode has been sent to the disk first before the deallocation has been sent to the disk. Right? This is obviously a wrong a wrong file system, a file system in which crash consistency has not been present. And so in order to maintain crash consistency of file systems, you require the truncate of the old file to be ordered before the write of the new file. So why does this affect streams? Now consider that you had written a large amount of data before the truncate, and you're trying to do an fsync after writing to the new file. You again end up with taking 4 seconds for the fsync because of you have this additional ordering, right? So essentially, the ordering required for file system consistency plus the ordering required for streams approximately achieves all the bad effects of global ordering. So if you are going to build a streamfs, a stream-based file system, then you need to take care of these dependencies. You need to change the file system structures and the file system consistency technique to make sure that such additional orderings are not present. That is one challenge. The second challenge is the semantics of stream-based ordering, right? So let us say you have one stream creating folder A and directory A, and another stream creating file or a directory B inside A. Obviously, you cannot create /A/B without creating /A. So how do you deal with this situation? This is a semantic question. We need to examine applications. We need to find out what applications implicitly expect to and impose those semantics on a string-based file system. And in some cases, the semantics can be useful to maintain intuitiveness, and in other cases, the semantics are a required part to achieve file system consistency. If you decide to allow the creation of /A/B without the creation of /A, you might end up with unused blocks on the disk being marked used. And in many cases, the semantic dependencies can be unclear. Like, for example, if you have two different streams appending to the end of a file, what should you do? Should you allow them to proceed parallelly? Do you make dependencies between them, and so on? StreamFS is ongoing work. There are many other challenges. We haven't solved all of them yet. We know what the challenges are right now. I would like your comments on whether you think this would be a useful file system. And there are, yeah. So to conclude, file systems vary a lot in their behavior that affects application level crash consistency. And the frightening fact is that the implementation details of the file system affect behavior, affect application level behavior. A lot of application protocols are complex and hence they are vulnerable. Many of them depend by design or by accident on the file system's implementation. And we have we are working on a file system that would help applications achieve crash consistency correctly. Before I end the talk, here is the kind of experiences we have when we discuss our vulnerabilities with application developers. Application developers usually say POSIX does not let you do that, and then we ask them, can you point us to the exact documentation? And they say, we cannot find it. So that's one thing. And here is the kind of experience we have with academics. They also reply that real file systems don't do that. And then when we point to them one particular file system which does it, you can read it. Anyway, so yeah, that's my talk. The Alice tool is available online. You can download it and you can go and examine your application and find out whether it would work properly on top of all file systems you would run it in. Thank you.